Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/JEDI. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you'd like to make a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's the problem for today, for July 14th, 2018. This is problem number 5 from the written answer section of the Spring 2018 exam MLC. An insurer issues identical fully continuous whole life policies to a number of independent lives, each age 80. The death benefit is $10,000. You are given, and policyholders will purchase the insurance. There are no expenses. The annual premium rate is P. LJ denotes the present value of the loss at issue of the Jth policy in the portfolio, and L equal to the sum of all LJs from 1 to n denotes the total loss at issue for the portfolio. The force of interest is 5%. You are also given the values of A bar 80 for various levels of the force of interest: 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.10, 0.11, and 0.12. Part A. The standard deviation of L can be written in the form square root of n times A plus BP. Calculate A and B. Part 2 of Part A. Show that the risk within the portfolio as measured by the total loss L is diversifiable. The insurer sets the premium rate at P equal to $1,300. Immediately after issuing the policies, it is announced that a new drug has been developed which may dramatically reduce mortality of the policyholders. There is a 60% chance that the drug will not work and the force of mortality will be unchanged, and a 40% chance that the force of mortality will be reduced by 0.01 for all lives in the group at all ages. Now, notice this is very important, that it's not the randomness is not at the level of each individual, but either the drug doesn't work for everybody or it works for everybody. It's not that it may work for one person and not work for another. It either works or it doesn't work for everybody. Part B1. Show that the standard deviation of LJ, assuming that the drug does not work, is 5,900 to the nearest 50. You should calculate the value to the nearest 1. Part 2. Show that the standard deviation of LJ, assuming that the drug does work, is 5,950 to the nearest 50. You should calculate the value to the nearest 1. Part 3. The insurer sells 400 policies. Calculate the standard deviation of the total loss at issue, L. Part C. Show that the risk within the portfolio as measured by the total loss, L, is no longer diversifiable. D. Explain why the introduction of the new drug has created non-diversifiable risk. For Part A, we have that LJ is equal to 10,000 e to the minus 0.05 T80 minus P A bar angle T80. And then we write A bar angle T80 as 1 minus e to the minus 0.05 T80 over 0.05. Recalculate everything, and this becomes 10,000 plus 20P. 20 is the 1 over 0.05 times e to the minus 0.05 T80 minus 20P. Therefore, if we write Z for the random present value of a unit death benefit for the same plan of life insurance, the variance of LJ is 10,000 plus 20P squared, the whole quantity, times the variance of Z. So it's 10,000 plus 20P squared times 2A bar 80 minus A bar 80 squared. Because L is the sum of n independent identically distributed random losses Lj, the variance of L is n times the variance of Lj, so it's n times the quantity we just calculated. And the standard deviation of L is the square root of n times 10,000 plus 20p times this variance of a unit life insurance. I'm sorry, not variance, standard deviation, the square root of the variance. We also have A bar 80 is equal to 1 minus 0.05 little a bar 80. So we can calculate it to be 0.72025. And 2a bar 80, it's a bar 80 at double the force of interest, so at 10%. So it's 1 minus 0.10 times a bar x with x equal to 80. I'm sorry, it shouldn't say x. Let me correct it. So it's 1 minus 0.10 times a bar 80 at force of interest equal to 10%, which is given in the table, and we plug it in, we calculate to be 0.5456. This gives us the standard deviation of L to be square root of n times 10,000 plus 20p times the square root of 0.5456 minus 0.72025 squared, and that's approximately equal to a square root of n times 10,000 plus 20p times 0.163829, and then we can write it as square root of n times 1638.2899 plus 3.2765798 times p, so that a is equal to 1638.2899 and b is equal to 3.2765798. For n going to infinity, we would have this expression that we just calculated, square root of n times this quantity, divided by n, and go to 0. This means that as the number of policies increases, the risk per policy goes down, so the risk is diversifiable. Now let DDNW stand for drug does not work, and DDW stand for drug does work. We have the sigma Lj at DDNW equal to 10,000 plus 20p times 0.163829, and that's approximately 5897.8436, or almost exactly, very close to 5,900. Assuming DDW, the force of mortality becomes the previous force minus 0.01, and the probability of survival becomes e to the 0.01 t times the previous probability of survival from the calculation of the probability of survival as e to the minus integral of the force. So we have now that a bar 80 DDW at force of interest equal to 10% becomes the integral from 0 to plus infinity of TP 80 times e to the 0.01, times e to the minus 0.10 t dt. And that is actually a bar 80 DDNW at force of interest equal to 9%, which is given in the table as 4.725. And a bar 80 DDW at force of interest 5% becomes the integral from 0 to plus infinity of TP80 times e to the 0.01 t times e to the minus 0.05 t dt, and that's a bar 80 DDNW at force of interest equal to 4%, which is given in the table as 5.855. So that 2 big A bar 80 DDW becomes 1 minus 0.10 times 4.725, or 0.5275, and a bar 80 DDW becomes 1 minus 0.05 times 5.855, and that's 0.70725, and the standard deviation of z becomes the square root of 0.5275 minus 0.70724 squared. That's approximately 0.1652622, and this gives the standard deviation as a square root of Lj as a square root of the variance. Well, but it's really that 10,000 plus 20 times 1,300 times the standard deviation we just calculated, and that's 5,949.44, almost very close to 5,950. For the next part, it's important to notice that in this new model, if the drug works, it works for everyone in the group. So the prospective loss is either LDDNW, which is the sum of LJDDNW with probability 0.6, or it's the sum of LJDDW with probability 0.4. And therefore, the expected value of well, first Lj DDNW becomes negative 71, and expected value of Lj DDW uses the values of life insurance we just calculated in both cases, and that becomes a negative 539. And the variance of Lj DDNW is the variance that we actually effectively calculated in part A, and that's approximately 4 million, I'm sorry, 30, that is correct. It's 784,559, while the variance of LJDDW is the same, but with a different variance of life insurance, and that becomes 35,395,811. For N policies, therefore, we have the values that you see here. The expected value of LDDNW is minus 71N. For LDDW, it's minus 539N. And the variance, well, because these are independent policyholders, we just multiply N by the variances that we just calculated. So that the expected value of the overall loss is 0.6 times the first loss plus 0.4 times the second. It's negative 305N. And the second moment of L is weighted average of the two second moments, which we calculate by taking the variance plus the square of the mean for both of them. And what we get out of this calculation is 35,029,060 N plus 119,017.4 N squared. And the variance of the loss, therefore, is, well, the second moment minus the square of the first moment. And this comes out to be 35,029,060 N plus 25,992.4 N squared. And the standard deviation of the total loss at issue for N policies is the square root of that. When N equals 4, this becomes, 400. This becomes what you get when you plug in N equal to 400, and this is 171,808.7124. And then the standard deviation of the loss at issue divided by N now becomes an expression that doesn't go to 0 as N goes to infinity. Instead, it has a limit. The limit is the square root of 25,992.4. And this represents risk that cannot be diversified away. So for part D answer, the issue is that this new drug has created a situation where the same risk factor, new drug, is common to all policies in the portfolio. When the same risk factor is present for all insured persons, this does create a non-diversifiable risk. Please remember, this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies, and good luck on the test.